Good morning. This is Physics with Keith, a live physics tutorial. It's Saturday morning, 10 a.m. on the 26th of September. And I think this is the third session we've done of this new academic term, this new academic year. And I can see that we've got 2 people currently watching, which is great, but the numbers might not be up to date. So a little reminder, this is a live tutorial, and you can see there's the little, that side, there's a little box here that shows the chat window from YouTube, if you go onto the YouTube website. So anything you type into there will be forever embedded in this video here. And the reason why I've done that is so that when you watch the video back, it makes a bit more sense as the chat things come through. So please do get involved, do ask questions, do answer questions as we go through things, and that will make this session a lot more fun and hopefully a lot more educational as well. Now, at the end of last week, we were looking at efficiency, a little bit on efficiency, but we were... I can't remember if we did efficiency actually, I can check. But we looked at Sankey diagrams and we looked at energy transfers from one store to another. And in particular, we looked at what happens when you drop something and the work done in dropping something and using that to determine the speed the object hit the ground. And at the end of last week, one of you out there seemed a little unsure on it, wanted a little bit more help on that, so I thought we would start there today. And then, if there are no objections and no questions, we would make sure we've mopped up and finished off energy, and I think we're done. Maybe I'll just show you a couple more equations, but I'm not going to go into the detail of them because I want to do that a bit later. And then I thought we would start on the next topic, which is still part of energy transfer, but it's specifically to do with heat transfer. So, if you are out there in the internet, in cyberland, and you're watching this, please do get involved. Drop me a little message into the chat thing. I'll just type my hello world in here so you can see that come up hopefully on the right there. It looks like it has. So drop me a little message, say hello, let me know you're out there, and then we'll get cracking, we'll get started. Oh, Freya's here. Hello, good morning, Freya. So if there is anything you're not sure of, or anything that you want me to go through that I haven't mentioned, you're very welcome to ask. Please do into that chat window, or if you prefer not to do it quite so publicly, you can use the Facebook Messenger, and you can find me on Facebook by searching for Physics with Keith. This week I've had no messages come through requesting any help. Once again, we had somebody saying that they would send me a question, but then they didn't. So if you do want that sort of help during the week, pop me a message in and then we can go through it on Saturday. And even if you're not available on Saturday to actually watch it live, you'll be able to watch it back. So here we go. Let's start where we finished. If you imagine we have an object, maybe it's a ball, here it is, and it is some height above the ground. I should probably have mentioned that you might want your pencil, your paper, or a pen and paper, your calculator perhaps. Make sure you've got those with you. I'm sure you have. And it's above the ground. And let's pick a height. Let's say that it is 70 meters above the ground. And we're going to ignore air resistance here. And giving no other information whatsoever, no other information, I would like to know what speed it hits the ground. Now, I will give you some hints, but feel free to put your fingers in your ears if you're going to chug through it yourself and you don't think you want the hints. So the hints. Hint number 1. The energy stored when you are at the maximum height is your gravitational potential energy, which is the mass multiplied by the gravitational field strength multiplied by your height above the ground. And we know the height above the ground, and we know the gravitational field strength. I wonder if you can remember what it is. What we don't know is the mass. Now, all that energy that's been stored at the top is transferred to the kinetic energy store just before it hits the ground. That's the main store of energy. Its energy is kinetic energy, just as it hits the ground down here. So the amount of energy that was stored as gravitational potential energy will all be transferred to kinetic energy. And here's that equation for kinetic energy. And the speed is what we wanted, and we didn't have the mass. So if you're working through this at home with your fingers in your ears, hopefully you've got that step written down. Most exam boards would actually give you a mark just for writing that step. Then you would notice that you can cancel the mass. We don't actually need to know the mass, because there's a mass on each side. If we divide both sides by m, the masses cancel. And if the reason why you're not quite following is because of algebra, then let me know. We can go through some algebra practice. That's absolutely fine. I'm here to help you. So if it's an algebra thing, do let me know. And so if I rewrite this equation now, GH equals a half V squared, and we check what we've got. G we know, and I wonder if you remember the value of that. H we know, half is just a number, and V is what we want to find. And so there's only one unknown in that equation, which is V. So we'll make V the subject. Now there's different ways of doing this. Either you can rearrange it symbolically. Yes, G, Freya, you are correct. G is 10. We would need a unit with that. So let's write that down. G is 10. And you can either call it newtons per kilogram, which is the unit of gravitational field strength, but that is in fact equivalent to, I've run out of room next to me there, is equivalent to 10 meters per square second. They're equivalent units. We're not doing any real sort of mechanics yet with acceleration, so we'll stick with newtons per kilogram for now. So the easier way of rearranging this, which won't help you quite so much when you get to your A-level studies, but it's certainly going to help you with GCSE, the easier way is to substitute your numbers first. Students often find the numbers less intimidating than the letters. So G is 10, H is 70, so we can substitute that. The half is still a half, multiplied by V, which we don't know, and that V is squared. And now we've got a better understanding of what to do. V squared is multiplied by a half. So I have to divide by a half, which is the same as multiplying by 2 throughout, to get 2 times 10 times 70 equals V squared. And 2 times 10 times 70 is 1,400. I hope that's right. My mental arithmetic is not wonderful, so I jolly well hope that's right. Which is V squared. And then we can use our calculator at this stage, because we can say the square root of everything in this equation. So the square root of 1,400 is going to equal V, the square root everything. We plug that into our calculator. I mean, it's going to be 10 times the square root of 14. I can't think what the square root of 14 is. So I'll do it in my calculator. Hopefully I've got 37 and a bit. Hopefully 37 and a bit meters per second. Fingers crossed I didn't make an arithmetic mistake. 37 to two significant figure, let's call it 37. And it said speed, so we'll call it meters per second. Yeah, 37.4, that's what I got. Thank you, Fran. So that's our approach. So I will give you another one. Give you another one of these where I'm not going to give you the mass, and I'm going to want to know the speed it hits the ground. And what I want to encourage you to do is to work through all those steps yourself. So I won't leave them on the screen. I will hide them. I will scroll down and I'll give you the new problem. But I do want you to work through all those steps yourself, because all of those steps would be needed to get your mark. Now, okay, with some of this algebra, some of this arithmetic, you can skip a few steps if you get confidence with it, but if you're not confident with the arithmetic, then please don't feel bad about having to put all those steps in. It's good practice, and it's by using all those steps that you will gain the confidence. So let's zoom back in to 100% and let's give ourselves a new height. And what I don't want you to do is just to go straight to that equation that I got for you and just plug the number in. I want you to go from scratch again. I think that's healthy. So let's go from 50 meters now. And I would like to know how fast it hits the ground. Very typical GCSE question. I'll work it out at the same time. I've left my calculator at work, so I'm afraid I'm having to use my calculator on my phone, which isn't ideal, but it's okay. So. So hopefully you're there, chugging away, working through the mathematics, writing it step down, then maybe plugging it into your calculator, seeing what you get. That's exactly what I got, Freya. Good stuff. The unit, however, is incorrect, I'm afraid. So you've written the unit m/s², meters per second squared, which is acceleration. A speed is how far, yeah, okay, it was just a simple slip, wasn't it? Yeah, speed is how far you go in a certain time, so distance divided by time, meters per second. Yeah, simple slip. But yeah, the answer, 31.6 to three significant figures, meters per second. Great stuff. So anyone else watching, I can see there's 3 people watching at home. Anyone else there, please do get involved, do join in. I think we're probably safe to move on now, having done efficiency and everything else. What I'll do is I'll just write on this board now a summary of all of the equations for energy. And most of these I think you'll have met. A few of these you might not have done. I'm just going to quickly scroll up and have a check and see whether we included the equation for power. Yes, we did. I can see that there on the right. So, all of the equations for energy that we have done in these last 3 weeks. We've got the definition of work done, which is a force multiplied by a displacement. And I'm using an S for displacement. Just scroll up to check I'm not making it up, and we did actually cover that. I might be making that up. I don't think we did cover that. My apologies. So there's a new equation for you. An amount of work that is done, that's equivalent to the amount of energy that's transferred, it's just a technical name for energy transferred, is equal to a force that is being applied multiplied by a distance over which that force is acting. So this is energy transferred. Spelled transferred wrong. Transferred. I don't know how many R's are in transferred. In joules. I think I'm missing an R there. Force in newtons. And this S. I know you think S might be speed. I'm afraid in physics that would be far too straightforward. And for reasons that I've never quite got my head around, this is what we call displacement, or a distance in a particular direction. And the direction of that displacement is the same as the direction of the force. So importantly, these two have to be the same direction. or if they're opposite directions, then you'll get a negative value, but let's not worry about that. So the way that equation works is if you imagine I have a box on a surface, and the surface has some friction. So let's imagine there's a box on a friction surface. There it is. Let's have it touching, shall we? There we go. And let's imagine that I'm pushing this box along at a constant speed. So I'm travelling at a constant speed. And if I push that box a distance, let's say 10 meters, and in order to push that box 10 meters, I have to apply a force, or I am applying a force in those 10 meters of, let's say, 3 newtons, then because I'm going at a constant speed, I'm not actually increasing the amount of kinetic energy in the box. So what's happening to all that energy I'm putting into the box? Well, because of the force of friction, the energy is going to be dissipated as heat energy. And how much heat energy is dissipated, I can calculate using this equation. The force is horizontal. I'm displacing the box horizontally. So force, 3 newtons times displacement, 10. I've gone behind my face. Please do let me know if I do that, because I get so excited sometimes I forget that my head's in the way. There we go. So force multiplied by displacement, this would be 30 joules of energy. Now what if I pushed the box with half of the force, but I pushed it across the same distance, but I just pushed it with half the force? What would happen to the amount of energy I dissipated as heat? I push the box with half the force, but I push it the same 10 meters. I just don't push it as hard. I push it with half the force, maybe 1.5 newtons. What happened to the energy I dissipate? Looking at the equation. Oh dear, we've gone down to just one live viewer. Oh, we have two live viewers again. Someone's come back. So half the force. I'll give you the answer because number of live viewers just suddenly dropped off. So if there were people watching, they may have missed the question. If I have half the force, I've done half the amount of work, which means half of the amount of energy is being transferred to heat. In other words, if I push it less hard, going along pushing it less hard, what's going to happen is I am going to waste less energy as heat by moving this thing. And that's interesting. That means if I move it slowly, it's less wasteful in terms of energy. If things are moving fast, it's more wasteful in terms of energy. And that's the same when you're driving a car. When you're driving a car down a motorway at 70 miles an hour, it uses a lot more fuel to go a certain distance as it would going at 30 miles an hour through the town, going the same distance. You're going faster, therefore more force is needed because as you go faster, air resistance is greater, so you need more force to be going at that constant speed that's faster, and therefore more work is done. But that work is done heating up the air, heating up the ground in the case of sliding the block along. So that's why it's not always a good idea to race down the road at 70 miles an hour. Anyway, so that's the first equation, and it really is as simple as that. You don't have to make it too complicated. So I'll write that down again. Work done, force multiplied by displacement. We then met some other equations. We met the energy that's stored in the gravitational potential energy store, and there's different symbols you can use for this, was mgh. We met that the kinetic energy was 1/2 mv squared, and we met the idea that power is the rate that energy is transferred, so energy divided by time. We also met efficiency, which was the useful energy output divided by the total energy input, or you can write it in terms of power, the useful power output divided by the total power input, and that doesn't have a unit. And I think that's it. I think those are the 5 equations we've met so far. So I'm going to add another equation, or another 2 equations onto this. The elastic potential energy is half k E squared, and we haven't actually covered what k means yet. That's the spring constant. And when we talk about forces, I spelled constant wrong. When we talk about forces, we will go into detail about what the spring constant means and what this extension on a spring means. So when we discuss forces and springs, this equation for energy will crop up as well. But I'm just popping it here so it's all in the same place in energy equations. There's another energy equation. The energy transferred in increasing something's temperature is equal to the body's mass, its specific heat capacity, and its change in temperature. Now, it's often written like this with a Greek letter theta. Greek letter theta, which is the change, well, delta theta is the change in temperature in either degrees Celsius or Kelvin. We don't know what all that means yet. That's the change in temperature. This thing called C is the specific heat capacity. And we'll talk about what that means at the appropriate time. Capacity. Mass is M, and E, I prefer to put a little delta before the E here, because having an equation with one delta in it bugs me. But that doesn't matter. I'll leave it like this. This is the energy transferred in heating something. So we could call this the heat energy, measured in joules. And that's it. That's all of the energy equations that you could meet. There's possibly one more you could include here, which is power equals current times voltage, which you might include in energy, but when we do circuits we'll cover that. So let's leave that one off for now. And GCSEs expect you to memorise most of these. You'll have to memorise this one, this one, this one, this one. You may have to memorise this one. You may have to memorise this one. It depends on which exam board you do. I don't think you have to memorise this one. So, but you still have to be able to use it. So what I wanted to do is have a little look. We're going to step across now to heat energy, and how we can transfer heat energy. Now, it's been a while since anyone commented, so I do wonder whether you're still out there. We did a couple of questions. It says there are 3 concurrent viewers right now. So there are people out there. Are there any more questions about energy and these basic equations, or do you want to practice some of these equations, or are you happy to move on to something with some simulations where we talk about energy transfer through heating? I'd rather go into energy transfer through heating because I've got those virtual physics lab simulations to show you. Happy to move on? That's great, thank you, Freya. And in the absence of any other comments, we will move on. So, what we've got is simulations that a chap called John Nunn has made from the National Physical Laboratory, and he's given me permission to use these simulations in these tutorials and in my YouTube videos. It's very kind of him, but he said as long as I give his website a plug. So if you search for Virtual Physics Laboratory on YouTube, on Google, Virtual Physics Laboratory, you can find everything about this project. The license to use this software is free for teachers who have been trained how to use the software. The license for anyone else, I think you would have to purchase. I don't imagine it's very expensive. But there's a suite full of simulations, and most of them are aimed at advanced level physics, A-level physics, but some of them, like the 3 I'm going to show you today, are perfectly suitable for GCSE. So what I'm going to show you is how heat conduction works. I'm afraid there aren't going to be many questions I can ask during this, but I might ask you every now and then, what do you think will happen if, and we'll see what you're thinking, just because it keeps you involved. So, what we've got here is a metal bar. Above here we've got a graph that shows temperature on the y-axis. On the x-axis is the position along the bar. And what I can do, there will be a switch somewhere where I can change the colour system for the bar. This is just a false colour. I can either have it so cold metal bar is blue, hot metal bar is red, medium metal bar is green, or I can have it so that it's just normal colour, and as it heats up it starts to glow red. I'm going to use the false colour because it really does help to show what I'm talking about, but this isn't actually the colour. I mean, you know this, the metal bar doesn't actually start blue and then go green as you heat it up. Now the temperature of the surroundings is here, and I have the option to either insulate or to uninsulate the metal bar. Leave it bare. If the metal bar is insulated, it's got a layer of something around it that reduces the rate heat leaves the metal bar. And if it's bare, then that layer is missing, so it's exposed to the air. This thing over here, this dial called conductivity, you can change this so it shows what happens if you use different materials. Conductivity is how easy it is for heat to move through that bar. So the higher the conductivity, the quicker we're expecting the heat energy to be transferred from where I put the heat energy to where the heat energy ends up. And so I'm going to put the heat energy in here by turning on a Bunsen burner. And if the conductivity was low, the heat wouldn't be able to conduct very quickly away. At the moment it's on quite high. So, let's turn it on and see what happens. So rather, as you might expect, where the heat is, it's getting very hot, but then you've got it cooler still at the edges. But if we watch one particular point on this bar, let's just watch here. Can you see how the temperature is starting to increase? If I put my cursor where the temperature is at the moment, it's there, and we just wait for a while I'm talking, you'll see that yellow line on the graph will go up and up and up and up and move away. But it's not going up very fast. And it almost looks like it's reached a steady state. Well, it's barely gone up at all. In fact, the end of the bar's almost the same temperature as it was before. So my question is, why is it that I'm putting heat into this bar, but the bar doesn't seem to be getting any hotter now? What do you think? I'm putting heat in, but the bar's getting no hotter. What do you think's going on here? Six people have clicked the link. 4 people are still currently watching, but one of those is me. So 3 people are watching. So, Freya says, because the heat is escaping at the same rate it's going in. What a good answer. What a fantastic answer. Yeah. The rate that the heat is going in. And rate in physics is a technical term that means the amount of something per amount of time. So the amount of heat going in a certain amount of time is the same as the amount of heat coming out in the same amount of time. What a good answer. So my question is, what will happen if I insulate this bar? What do you think is going to happen then? Tell you what, doing these online tutorials will make you very good at typing, won't they? There'll be more heat going in than coming out. Perfect. So tell me what will happen to the temperature of the bar at some point, perhaps over here, where at the moment it's nice and cool. I can still touch the bar at that end. It will increase. And of course it will. So let's wrap it in insulation and let's watch that happen. So wrap it in insulation. There's my cursor. And now you can really quite clearly see it's starting to creep up. The bit where the flame is has gone off the scale in terms of temperature now. It's gone black, it's gone off the scale. And yeah, we can see very clearly the temperature is now increasing at all points along that bar. If you look at the colours along the bar, you can see the green spreading towards the right. You can see the yellow starting to spread towards the right. That blue, that pale blue, cyan colour is moving towards the right. There is no ambiguity here. The temperature of the bar is increasing. But importantly, the heat is moving from where we put it outwards along the bar. And we need to understand the mechanism for that heat to move. So do you know how an increase in temperature manifests in a material? So what I mean by that is if I have two materials that are exactly the same, but one of them has a higher temperature, what's actually happening in that second material that's at a higher temperature? What is this thing called temperature? Do you know? It's a tricky question. The atoms are vibrating more. Again, a very, very good answer. I get the feeling you studied this before. This is very good. So, new part of our notes. Let's put thermal physics. I'm going to go ahead and undo a little bit. Yeah, that's good. That's good. So if we've got two bodies here that are identical, absolutely identical, what you've told me is that the particles in the hotter body, the one with the larger temperature, are vibrating more. The atoms, should I say, are vibrating more. Let's call this temperature 1 and this temperature 2. And let's suppose that temperature 2 is greater than temperature 1. So we've got our atoms inside here. I'm a bit lazy, so I'm not going to draw lots of them. And they're in a nice regular pattern, as you can clearly see I've not drawn. And we're saying that they're exactly the same substance, but the one on the right is shaking a bit more. And you are right. What do you call the energy store when something shakes, when something moves? What do we call that energy store? The energy store for moving things. Kinetic, absolutely right. And so what we could say is that in this right-hand one, the kinetic energy store for the atoms is higher. And I think that's okay. I think we can agree with that. Each atom, if it's moving faster, it has more kinetic energy. So there's a technical definition of temperature, which I could tell you the temperature is equal to the average kinetic energy per particle in our system divided by the number of degrees of freedom in our system. But you don't need to know that for GCSE. What you need to know is this, that temperature is related to, that's a nice vague way of saying there's some sort of relation there, related to the average kinetic energy of, and I keep saying particles. Particle means the smallest the smallest chunk of matter that's the same type of matter. So a particle of water is a molecule H2O. You can get lots and lots of particles of water together, but once you get an H2O molecule, if you break that down any smaller, it's not water anymore. So a particle of water is a molecule of H2O. A particle of helium gas is an atom of helium. A particle of cathode ray is an electron. So what makes something a particle is if it's the smallest chunk of matter of a particular type of matter. So I'm using the general term particle here. Temperature related to average kinetic energy of particles. Which means that if I add up the kinetic energy of each particle and divide by how many particles I've got, a higher temperature will have a bigger number if it's the same type of substance. So let's give you a quick puzzle then. Let's imagine I've got a very big substance here, a very small one. Okay, and I'm trying to draw these to scale roughly, so you can see the squares on my grid. the let's try and get this right. This one on the left has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So it's 7 by 7. Is that 7? Is that 8? 1, 2, 3, 4, 5, 6, 7. 8 by 7 squares. Oh, I'm not very good at my 8 or my 7 times table. What's 8 times 7? The one on the left has 1 square. 8 times 7. We can do this. So 4 times 7, 14, 28, 40, 56, I think. Yeah, thank you, Freya, 56. So 56 particles, this one's got 1 particle. So it's all to scale, okay? Let's imagine that I give the one on the left an amount of energy, kinetic energy. I push the molecules, all 56 molecules, and give them, the whole box gets 1 joule. And on the left, I give it 1 joule. The amount of heat energy I've put in each box is the same. Which box has had the higher temperature increase? They both have the same amount of heat put in, but as you say, the small one's got the higher temperature increase because the average kinetic energy per particle will have increased more for the smaller one. Exactly right. Let's flip this question on its head. Let's imagine we've got an iceberg. I'm not an artist, so this is going to look a little bit shaky. An iceberg, quality, and I've got a small glass of boiling water. And I'm going to have me holding, maybe I'm stood on a life raft or something, I don't know. Small glass of boiling water. So here's my boiling water. A small glass. And here, this is not to scale. Icebergs are enormous. This is a huge iceberg. Which one is colder? Simple question to start with, and I think you'll definitely know the answer. Yep, the iceberg's definitely colder, which means that its temperature is lower. So when we say hot or cold, we mean lower temperature. But which one, and I'll put down here, equals higher temperature, which one has more thermal energy, more heat energy inside it? What one do you think? An enormous multiple ton iceberg that's colder, or a cup of boiling water which is hotter? But which one actually has more thermal energy? Hey, Lex has joined in. Good to see you, Lex. Yep. So the iceberg, both of you are right. The iceberg has more heat energy because although the cup of water has more kinetic energy per particle, per molecule of water, there are a hell of a lot more molecules of water in the iceberg. So the iceberg overall has a lot more energy. And that's a weird idea to get your head around. But when we say we heat something up, do we mean we increase its temperature, or do we mean we put heat energy in? And the two aren't quite the same. And that is why in physics you might see questions that talk about heating it up. They're very, very badly written. Decent physicists, decent physics teachers in particular, try to avoid terms like heating things up unless they are being deliberately vague to obfuscate what they're asking. Anyway, heating something up, does it mean increasing temperature, or does it mean putting heat energy in? Because you can put heat energy into something and its temperature doesn't change at all. I know, we'll come to that. We're not there yet. So, conduction then. We now have a better understanding of what temperature is. It's related to this kinetic energy of the particles. Particles are shaking about. So let's put these two boxes together. When we put these two boxes together so they are in physical contact, let's draw my box and draw another box. These are now in physical contact. These are the same two boxes as I started with. T1 and T2, where T2 is a higher temperature than T1, in which direction is the heat going to move? Whatever this abstract concept of heat is, in which direction is it going to move? I can't quite get them perfectly to line up. Is it going to move from left to right or right to left? It's going to move left, yes, it's going to move from right to left. So the heat is going to be moving in this direction here, into T1, perfect. Which direction are the particles going to move? Yep, Lex agrees, T2 to T1. Which direction are the particles going to move? I'm hoping you're all getting confused by that question. They can stay where they are. Of course they are, Freya. They can stay where they are. They're shaking, but they're going to stay where they are. So what's happening to transfer this heat? There isn't actually something physically moving from right to left. What's happening is the particles on the left are colliding more frequently, and on the boundary between these two different temperatures, if you've got something on the right, did I say left? Sorry, I meant right. If you've got something on the right colliding more frequently against the thing on the left, it's going to transfer energy preferentially in that direction. If I try and give you an example, imagine we're doing some bumper cars, or dodgems if you prefer, and there's two dodgems sat there facing each other here and here, and they decide to bang into each other. And the one on the left tries to bang into the one on the right, and it goes forward and it pushes itself forward once every minute. But the one on the left is going to push itself maybe 5 times a minute. It's going to keep on banging into the one on the right. Now they're going to collide the same number of times, because each time they touch, they're colliding. But the one on the the one on the left is moving 5 times a minute. The one on the right is moving once a minute. Overall, what's going to happen? This whole lot is going to move that way. Okay, bad analogy, because bumper cars can actually move. But this one's going to be transferring its kinetic energy over to this one 5 times in a minute, whereas this one's going to do it backwards once in a minute. Really bad, and I don't like that analogy. Can we use a Men in Black style memory eraser and get rid of that analogy? Because I'm not convinced that works. So, Men in Black memory eraser. There we go. Get rid of that analogy, I don't like it. So the heat's going to move this way because of the way the collisions are. There's another mechanism for transferring heat that metals can use that non-metals can't. So what do metals have that non-metals don't have that might make metals better conductors of heat than non-metals? What do metals have that non-metals don't have? I think the bumper car analogy does work as long as the car that's not choosing to collide stays still at the time, but then the matter still moves, and I'm not happy with that analogy, no. A molecule lattice, the thingy, yeah, I know what you're trying to say, Freya. The thing is, the non-metals can also have that as well. You get crystals of non-metals as well as crystals of metals, which is, I think was what you're referring to. Lattice of molecules is what forms what we call a crystal. And you get non-metallic crystals. Lex has got it, where he says free-floating electrons. We might call those delocalized electrons, or electrons that are not bound to atoms. That's how you can get electrical conduction with these delocalized electrons. In metals, you might have heard it referred to as a sea of electrons that exists between metals, bonding the atoms within a metal together. Have you heard the term sea of electrons? I wonder. Ah, yes, you remember. Good. So sea of electrons. So I want you to imagine you've got some sort of I suppose the example would be a mosh pit. So you've got lots of people here dancing aggressively and banging into each other. If you've ever seen a mosh pit, it's a type of dancing which is popular with certain genres of music that I happen to enjoy. So these lot are here, they're moshing away, they're enjoying themselves, and over here is some people that don't want to mosh. What I'll do is I'll colour those in a different colour. So the non-moshing ones, these are the spectators. they're at a gig, maybe it's a Machine Head gig, and just come on and started playing something brilliant. And everyone over here on the right just wants to enjoy the show, and everyone on the left wants to dance aggressively and bang into each other. And what's going to happen is the ones on the left, by banging into the ones on the right, are going to force the ones on the right to start to move in a way they weren't moving before. But what would happen if the ones that were all given balls to throw at each other as well? Cricket balls. I mean, this is going to become quite a violent massacre, and the police will have to get involved, probably a bad example. But they will start throwing balls around as well. The ones on the left are much more energetic, so they're throwing the balls far more than the ones on the right, and the balls are not restricted to banging into the people immediately next to them. The balls can go like this. They can be thrown great distances. So that's a second mechanism of transferring kinetic energy, by throwing a ball from one side of the mosh pit to the other. I'm talking to children who probably have no experience of mosh pits. My apologies. I would say go look it up on YouTube, but that's probably a mistake. But you get the idea. Violent dancing, banging into each other. And if you add a second way of transferring kinetic energy, you can more quickly get those on the right to join in with the dancing. The bouncers will kick you out, and rightly so, but it would work. Yeah, Freya says she's no idea. Her mum agrees. yeah, okay. I'm 36. I've spent a lot of time in a lot of mosh pits. So that's what's happening in metals. You've got these electrons that also can get right the way across that lattice, and they can go between those molecules, carrying their kinetic energy with them and delivering it the other end of the lattice, which is at a lower temperature, and therefore the kinetic energy is lower. And this average movement of this kinetic energy through the lattice is from the direction from the hot to the cold. But you do get energy going the other way, just less rapidly, because they're not throwing their cricket balls quite as energetically. Yeah, that really was a bad analogy, but I'm not going to use the Men in Black memory erasing thing on that one. So that's conduction, I reckon, done. I've just looked at the clock. My goodness me, I've been rambling on for a long time. I did want to just finish off convection and radiation as well, but I think we might have to leave that for another time. That's now so hot, the temperature's gone off the scale on the graph, and the whole bar has gone black off the scale. Whoops. Let's turn that off. So that was conduction covered. I think what we'll do is we'll put a pin in that, and we'll start next week with convection and radiation. And I don't imagine we'll get a lot of time to move on to the equations for thermal energy, for specific heat capacity and things. I don't think we'll get onto them next time. We might just touch on it. We will see. But these are the two simulations I want to show you next week then. The effect of radiation. So what happens when you make an object hot? It doesn't just get hot, it emits radiation. We'll play with that next week. And what happens if we make a fluid hot fluid becomes less dense, rises up. Okay, I'm going to stop. I'm going to have to stop. Right, are there any questions? Now's your chance. It doesn't have to be about thermal physics, and it doesn't have to be about the energy stuff that we've just mopped up and finished off this morning. Are there any other areas of physics that you really do want to quickly go through? No questions from Freya? Or Lex, have you got anything you're confused or concerned about? I know, Freya, you've not got any tests coming up. Lex, I don't think you've got any tests coming up, because your dad told me about what's going on in your school in terms of delivering physics education, so I don't think you've got any tests coming up. Right, okay, then let me show you one last thing. You've got chemistry coming up. Well, I can't help you with that. I know nothing about chemistry. I'm not even convinced I understand the periodic table. Thank you. My first lesson in physics since... someone new. Hello, David. Well, welcome. I hope you found that entertaining. No physics. You've got an astronomy test coming up. Now I don't have very much astronomy revision resources that I could send you, Freya. I'll have to have a think about that. I might send you something over via the Facebook Messenger, or via your mum via Facebook Messenger. What I want to point out to you all is the Isaac Physics website, which if you joined in during the summer, where is it? There it is. If you joined in during the summer the summer school session, then you will have had some experience with this. If you haven't, then this might be new to you. What I might do is set you some assignments on the Isaac Physics. Isaac Physics, if you don't know, I would say that it's completely nothing to do with me. However, I'm afraid, well, not afraid, I'm very proud to say that I do have some involvement with it. Certainly not anything to do with the website, which is amazing. I wrote some questions for it. That's about where my involvement stops. So that, and I do some boot camps and tutorials for A-level physics with it, and things like that. But the project itself is much, much bigger than me. It's a wonderful project. But on Isaac Physics, if you log in to an Isaac Physics, sign up for free, you can find all these questions. If you click on GCSE, there's a book that you can purchase. It's £1. It's not expensive. Or you don't actually have to purchase it at all, because you can, you see that's my name there. You don't have to purchase it at all. All the questions are freely available online. So if, say, we're looking at energy, and you want to have a look at some questions about efficiency, perhaps you weren't quite sure you understood the equation, you can click View Board, and then you can work through these questions. So if you see a question like that, you try and get the answer, you type what you think the answer is, you select your unit, and you click Check My Answer, and if it's wrong, it will tell you, and if you're right, it will tell you. And what's quite nice about this is there's some hints. If you click the hint at the bottom, you can see some notes about efficiency, which you can read, all about efficiency. The equations haven't quite formatted right there by the looks of it. I might have to report that onto them. But also there's usually a video that you can watch, which will give you some guidance on how to answer these sorts of questions. So you can see here someone called Lewis Matheson is going through Sankey diagrams. So there's a lot of things on the Isaac Physics website that is going to help you, and I thoroughly recommend it. Listening to me talk is great, going through a few questions with me is great, but that's half an hour to an hour a week, probably isn't going to cut it. But if you follow through Isaac Physics, you're going to have so much question practice. In your GCSE, about half of your GCSE is just going to be maths, using the right equation, getting the right answer. And you can get that skill, you can develop that skill, you can master that skill yourself just by working through Isaac Physics. I reckon you can get a grade 5 or a 6 just with the Isaac Physics practice. So I recommend it thoroughly. Anyway, thank you very much, Freya, Lex, David, welcome. And anyone else who was watching live. I'm going to turn this off now. Have a lovely week. Send me any questions as they come up through the week via Facebook Messenger, and I can respond to you. If it's a quick one, I can just send you a response. If it's not a quick one, or it's something that needs a bit more interaction, then I will store them up and we can talk about them next week. We'll start next week on energy, on thermal physics. We'll finish off thermal physics next week, maybe without the equations. I'm repeating myself. I'm going to stop. Have a good week. Stay safe, and I'll see you later.